All right, is this loud enough for everybody? Are you ready to shout it at about Hadoop and not Hadoop? Okay, cool. It's, according to my internal clock, this is like nap time for me. Might be for some of you after lunch. So I'm gonna try my best to make this fun and entertaining, and there's some terrible puns in here, so that if you're falling asleep, you all have no choice but to wake up and tell me how terrible they are. So all the slides for this talk I just posted on Twitter. I'm at Boykis. And this talk is about me talking you down from the ledge of distributed systems and back into the safety of your local machine. So just a little bit about me. I work as a consultant at CapTech. We do IT consulting. I work specifically in data science and engineering. So I do a lot of projects around data movement into distributed systems. And as I've been working on that, I've noticed that there are some pain points that working on not distributed systems can solve if you use them correctly. So that's what the talk is about. Personally, I primarily work a lot with Spark, Python, SQL, Stack Overflow, command line. That's my main stack. And I'm also on GitHub, Twitter, if you want me to send me jokes about how terrible my puns are. Okay, so we're going to talk about how your computer is good enough to do a lot of data processing that you're thinking about doing, whether to decide whether you actually have big data so you can make a leap to a distributed platform. And then we're going to talk about a module in Python called Multiprocessing that can make stuff faster. So if you just saw the Dask presentation that Matthew Rockland gave, he gave like the BMW of distributed systems local processing. We're going to scale it back. This is like the Civic, the Honda Civic of multiprocessing on your laptop. And then we'll talk a little bit, if we have time, about when you actually do need distributed systems and what they make sense for. So, okay, so the birds, you know, to everything, turn, turn, there's a season. There's a time for distributed systems, and there's a time for local processing. And as a data person or a developer, it's your responsibility to understand when you need to use one or the other and come to that place of healing away from the big data system pain. So we're going to be working on my local environment. I just have a 2015 MacBook Pro. Nothing special. It has a quad-core processor and 16 gigs of RAM, and that's going to become important because the cores tell you how much processing you can actually do. So quad-core, again, means you have one CPU and 4 cores, which you can run 4 processes truly in parallel at the same time. So if you're trying to do quick processing, you're bound by what's available to you. I noticed a lot of people have MacBooks here. Even if you have a Windows machine or Linux and a similar environment, you'll probably be able to get the same kinds of benchmarks that I am on any kind of modern machine. So let's say that your boss comes to you, and he or she says, please analyze Les Miserables for me. So this is obviously a pun on one of my favorite musicals, Les Miserables. And I did not pick this only because it is the best musical of all time. I also picked it because it's a pretty big data file. So one copy of Les Miserables is like the 3rd or 4th largest novel in the English language. So it's about 600,000, 700,000 words, or 3.2 megs for a single copy of this program. So your boss comes to you and says, I want you to count the words in Les Miserables, and I want you to do a word frequency chart. So, of course, MapReduce, the most common programming paradigm in distributed systems. But the thing is, you don't always have big data. You don't always have to go to the cloud. So there was a website, which no longer exists, unfortunately, called yourdatafitsinram.com. And you could basically go there and put in how much data you had, and it would compare that against the size of like a pretty big Dell server that you could run on a single machine, and it would say, you don't need distributed systems, you can do all your processing on this single server. So in working with data across different companies, I found that there's like a sweet spot to how much data needs to be processed. So if you're talking about kilobytes or megabytes like we have in our single Les Miserables file, you can probably even process it, I hate to say this, using Excel. So Excel is actually, in defense of Excel, it's a pretty good processor, and it can process up to 2 gigs of RAM. which means it can process about 1 million rows. And I think if you have 64-bit Excel, it can actually do even more. Once you get past that, it starts crashing. You start hating your life. So then you probably want to move on to the Python stack. So you could write your own Python code from scratch, which is what we're going to be doing. Or you could go to Python or to Pandas, processing chunks. Or you could even put your data locally in a database like Postgres. Or you could do command line operations. So up to about 1 gig or 2 of data, you can do all of this comfortably using these tools without ever leaving your local environment. Once you get to kind of the 10 gigs of data, 50 gigs of data, 100, you probably want to start considering distributed systems like Spark, like Hadoop, like Postgres on a server somewhere, like doing something in the cloud. And then once you get past 100 gigs to a terabyte and a petabyte, then you really do need distributed systems. And the other thing to think about is how fast, so the volume, variety, and velocity of data. How often are you having to process this data? Do you have a terabyte that you need to process once? Do you have gigabytes that you need to process time and time again? As the architect or the data person, it's going to be your job to kind of look at this scale and figure out what the right tool for the job is. So how much data can your laptop process locally? So Databricks, the company behind Spark, did some optimizations to the Spark engine. This was a blog post from last year. And they basically optimized it to the point where you could do 1 billion records, joins, and aggregations in a second on a single 2013 MacBook Pro. Now, they are a vendor, so it's their job to tell you how awesome they are. So take it with a grain of salt. But if they can do even a fraction of that, that's pretty awesome on a local machine. And then there was also a really good blog post a couple years back. The link is on Twitter. I posted the slides, where someone processed basically 2 gigs of data with 2 million chess games, and they used the find xargs mock, Unix command line utilities pipeline, and they were able to do it in 12 seconds, which was 235 times faster than the same Hadoop implementation of that problem. So it really depends on your tool set, what you have available, and the data. So you could potentially process a lot on your laptop if you optimize that process. So let's look at our file, back to Les Mis. Just do a head on it, just basic text file. Let's start with command line. So if we really wanted to, this is a pretty small file, so we could do a command line map reduce. So we have a pipeline where we process the data, clean it up, and then we group it together. So the first part, the first couple lines, sed is a text utility in Unix. It takes in the Les Miserables text file. It gets all the alphanumeric characters. It strips out the line breaks with spaces. It compresses the adjacent spacing. It converts everything to lowercase so that we can count all words the same way. It sorts the words alphabetically, and then the unique C is what really does the map reduce work. It counts the number of unique occurrences of each line. And then we can pipe that into a way to show this. So you can see that we get our word count for the one file. So we have Marius, who's a main character, and then John Valjean is part of a main character. So you can see their names come up, and then you get your token words, which you would probably parse out. So just with a sanity check, they are the main characters, so they appear the most often. So this seems pretty reasonable, and so here you have your word count in just like a single command line chain. Okay, so what if we have more than one Les Miserables file? So let's say we have 1,000 of these files, and so this is just a small bash script to basically replicate that file 1,000 times. So the original file size is 3.2, 3.3 megs. And after we did that replication, we came out to 3.2 gigs, which is now getting into medium data size, which is probably more than you want to process using a command line operation. So now we can actually get to writing some Python. So with command line, it's fantastic, it's great, it's really good for one-off tasks. You can't really see what's going on under the covers, and also Python is awesome. So now we're going to rewrite it, we're going to re-implement it in Python from scratch. So we have a script called mapreduce.py, and what that's going to do is the same kind of operations that the Unix commands did. So what we're going to do is we're going to get our text input, we're going to clean it up a little bit, we're going to process it, we're going to add it all together, we're going to count the occurrences in each file, and then we're going to aggregate all those files. So it's almost the same as we had before. We're just adding this reduce function. So again, we have a function called getFileNames. It's going to get all our text files. GetData is going to do the text processing and strip and split and all that stuff. The map function is going to count the unique occurrences of words in each file. And the reduce function is going to sum up all that stuff across the files. And then show items is going to spit that out. And all of this code is available in my GitHub repo. As we said before, we kind of skipped the non-glamorous part of text processing, which is like 80 to 90% of our daily work, just so it looks good in a presentation. So here is the actual. I did want to show the map and reduce. So what we have here is, map is going to take a single file name, so it's one process. It's going to take a list of words in that file, and it's going to try to add them to a dictionary. And if it doesn't exist, it's going to add them. So it's going to increment a counter. And then with the reduce, it's going to take a list of dictionaries, because we now have multiple map processes, so we need to kind of group them all together. It's going to iterate through that list and then through all of those dictionaries and then try to append to another dictionary if that word exists, and if it doesn't, add it. So that is essentially the entirety of MapReduce, and that is what big data has been based on for the last 5 years. So now you know the entire secret, and you can implement this from scratch. And if you kind of look at the reduce function, you can also do collections counter. That's an even easier way to implement it. I just wanted to show how you actually do the mechanics of it. So here's what we have passed in the map. So each file produces a dictionary. So we have a count for each file. And then the reduce is going to add up those counts across the file, so you get a most complete list of all of your words. So how long does it take to run this process? So here's the code that you would use to run it in a non-parallelized, non-optimized way. You would loop through the file names, you would put them into the map function, you would append them, and then you would do the reduce function on that list. So this function, with about 3.1, 3.2 gigs, takes about 5 minutes, 14 seconds. Time is a really nifty function that I learned about recently. It's really cool. Yeah, so that takes about 5 minutes, a little over 5 minutes. So how can we speed this up? Let's say, because it's going to grow exponentially, right? If we have 5 gigs of files or 10 gigs of files, it's going to take exponentially a longer time. So the way to do this is multiprocessing, and then on top of that, we can do PyPy. So in order to understand how multiprocessing works, we need to understand a little bit about threads and processes and GIL. So the way that Python works is it can run a single process, or it can run, it's bound by a single thread by a single process. So a process is a program. So if you think of a process as running a Word document, or running Excel, or running a notebook, right, a Jupyter notebook. Those are all examples of processes. In our case, a process is the MapReduce program itself. And then a process has sub-processes that it runs. So a sub-process is a thread. It's called a thread. And so our sub-processes are all the functions that we mapped out. So get file names, get data, map, reduce, and then show items. Each of those is a thread. And the way that Python was architected in the beginning was it has a global interpreter lock, which means it can only run one thread per process. So you can only do one thing at a time. So in this case, so the snakes are like blocking the other processes. Just imagine that. So you have get file names, which starts to run, and you can't run anything else, which means it's really slow because we potentially could run map in parallel, right? We could count the number of words per file, and we could do that for each file simultaneously, like we're not bound by any other process there. So that is slowing us down. That's why it makes it 5 minutes. And so if you run Python mapreduce.py, and you run the top command, which shows you what's actually going on as you run stuff, you can see that it's utilizing 99% of a CPU. So in this case, that's 1 core. And then the hashtag or pound th is the number of threads running. So this is what Python limits you to. So you can see that there's only 1 process running, which is really going to slow us down. So the way to solve this is we can use something really cool called a multiprocessing API, which allows you to treat each function call as a separate process. So you could potentially run tens or hundreds of processes at a time. So there's two things that you can use in the multiprocessing API. You can use process, which is pretty easy because you don't have to specify anything. So if you use process, basically process is in control, and it'll spin up however many processes it deems necessary. So it's good for really small things. It's probably not good if you're trying to process 1,000 files, because then you're just gonna crash your computer. And then there's pool, which allows you to control the number of processes that you have going on. It also allows you to control the size of the chunks that you pass into the processes. There's also map async, which we're not going to get into because that gets a little more complicated. But basically, the map function within pool is what we're going to be using because it's similar to what we've been doing. And map is a good paradigm to parallel process a lot of data. So here's what map actually takes. So it takes a function. It takes an iterable, and you can specify a chunk size if you want. So the way this works, so for ours, what we're doing is, so we're still getting the file names at the bottom here first. Then we're saying that let's say we want to do 5 processes at a time. We're going to pass in our map function to pool because that's what we want to parallel process. And then our iterable is the number of files. So we want to map over all our files in chunks instead of having to do it one by one. And we set the chunk size to 30. And I predetermined that this was a good size, but you will probably want to play around with it, with your code, to see what gives you the best performance. So you're splitting this up into 5 processes. And so each of those has a chunk size of 30. So each process is running 30 files through the map function at the same time, and then it's starting again. So you're really splitting up and parallelizing your tasks. And then we run everything through the reduce function. And then when we run top, then you can see that you actually have 5 Pythons. So it's simulating 5 Pythons. They're still each at a single thread, but now you can run 5 of them at the same time to speed up performance. So how long does this take? This cuts us down to a little bit under 3 minutes, and you can see that we get the same results. So if you think about, we had like 1,000 Valjans and Marius and Johns. So this is times 1,000. So now we're getting all of that same data back. And we just shaved 2 minutes off of our 5-minute job without any optimizations off the bat. So the other thing you can do is, if you want it to go really fast, it's Guido endorsed, is to use PyPy, which is an alternate processor, or an alternate interpreter. So Python uses CPython. You can use PyPy instead, and it does some optimizations under the covers. The trade-off here is, if you're like, well, if it's so fast, why can't I just use it for everything and just use it all the time? Because it takes a while to set up, because it's setting up those optimizations. So you want it to run mostly Python processes and on mostly Python code bases. So like if you have a mostly C code base, it won't optimize for that as well. And so if we run it through PyPy, it takes even less time. It takes 2 minutes, 10 seconds. And then let's say we have double the size of files. Let's say we have 6 gigs that we want to process. That entire process takes 4 minutes and 23 seconds with both the multiprocessing and the PyPy. Whereas before, when I just ran it straight through unoptimized, I had to stop after 13 minutes because I was really worried about my computer's fan. So this is a fantastic way to process data if it fits into what you're doing. So again, so you can process fairly large amounts of data, 5 to 10 gigs easily, locally, using multiprocessing. make sure that your code is structured for it. So our map function was really good because we needed to do a bunch of stuff at the same time. Like we didn't need to wait for other processes to finish, in which case you would probably move into async IO territory. And then you can also try different pool chunk size process optimizations. And then if you really want to speed it up, you might want to consider moving to PyPy, which would make it even faster. So that was walking you through how things work locally. So the whole point is that when you're thinking about a distributed system, all the stuff that we talked about, like setting the bucket size, the chunk size, rewriting the code to make sure that it was parallelizable, all that stuff happens in distributed systems, but it takes much longer, and it takes much longer to start them up. And so there's a really good paper about how an optimized single node, aka your machine, is better than multiple nodes. And so you could also do this using Spark locally, and it takes much less code. But what you're doing, so in a distributed system, so I just walked you through how the process works for Python. In a distributed system, what you're setting up, for example, in Spark, is you have the Spark context, then you have drivers, then you have executors. So you have a bunch of different things that are listening to each other and waiting for different aspects to finish, which is where a lot of the overhead comes in. So the code takes much less to write. So I think my code was like 110 lines or something for MapReduce. You could probably reduce it even further. This code takes much less time to write, but it takes much longer to run. So I think for this one, it took about 10 minutes to run with Spark locally. So again, what big data can't give you when you're thinking about moving to a big data system is any kind of consistency guarantees, data integrity, all of that stuff. But what it can give you, so I talked a lot about what we can do locally. What it can give you is, if you're thinking about moving, is a lot of storage of unstructured data. So again, up to that, so 10 gigs and more range. Fault tolerance and availability. If your single node machine goes down and you have stuff processed on your laptop, like that's it, you're gonna lose it. If you're working with a lot of other team members, it's a centralized place to store stuff. And it really gives you performance improvements up past that 10 gig mark. So those are just some things to think about. Let's see, I am actually early, so I will give you back some time, and I'm gonna stop there and pause for questions. Questions? Yep.
To what degree does that scale of size versus doing it on your laptop adjust for the libraries that people use on a day-to-day basis with Python, so pandas, for example?
What do you mean? Let me go back to that one.
So 10 gigabytes in pandas, and like how much RAM does that actually take up? On your computer, does that actually fit? Like in practice, what's the adjustment with the libraries that you use?
Yeah, for pandas, you could potentially fit a lot because pandas also allows you to chunk data. So I think I've done, I don't know what the largest I've done is. I think I've done maybe up to like 5 gigs in pandas. But I know people have done much more, but it becomes a little bit unwieldy like once you really start to get up there. Anyone else? Yep.
So how would you say the comparison between using the multiprocessing and PyPy versus running a single Python script and then using something like GNU Parallel?
Like GNU Parallel?
Yeah.
I don't know. That's a good question. I haven't used that, but that could be something you could explore and write a blog post about.
Lightning talk.
Lightning talk, yeah. Anyone else? Okay, cool.